don't know how to do.
Recording has started.
Okay, so thank you all for joining. Mattia replaced me, asked me to replace him as moderator today. I will introduce very shortly now Dr. Maxime Favier, which is now doing a postdoc in Paris at Collège de France, under the direction of Michel Brune and Clément Serrin. So he's working on circular Rydberg atoms for rubidium. Prior to this experience, Maxime Favier performed his PhD, always in Paris, at the Observatoire under the direction of Sébastien Sirte, where he managed to work and build a mercury optical lattice clock. After that, he fulfilled a first postdoc in Amsterdam, where he was working on QED benchmarking, in particular on precision spectroscopy of simple atomic systems. So I've been looking forward for this talk for a while now, at least a month. So I will leave the ground in a very few moments to Maxime. I invite you all to turn off your microphone and camera and keep it like that, unless you have questions, of course, so that we can hear properly. So Maxime, it's up to you, and thank you for being here.
Yeah, thank you, Andrea, for the kind introduction. One suggestion that I have is that maybe in the middle of the talk, maybe we can take a short break for questions if you want. That way people can ask their questions not all at once at the end of the talk. And if there are no questions, well, great. Okay, so good morning, everyone. I'm Maxime, and today I want to tell you a little bit about what we do in the lab in Paris in the group of Michel Brune. And the gist of it is that we use Rydberg atoms, and in particular circular Rydberg atoms, to build new quantum technologies. And let me just preface my talk with a quote from Erwin Schrödinger, which is in 1952 said that it's fair to say that we are not experimenting with single particles in the lab any more than we can raise ichthyosaura in the zoo. And just for fun, I put at the bottom here some artistic realizations of the Borowese group, where they build fancy Eiffel towers with single atoms. So I think this is only 70 years after Schrödinger told us that this was basically impossible. So I think atomic physics has a lot of unforeseen technological advances in store for us. And so let's see where we can push this. The outline of my talk will be the following. I will first tell you a little bit about Rydberg atoms, because I think not all of you are familiar with the concept. And I will focus, of course, a little bit more on circular Rydberg atoms, which is what we use in the lab. And then I will briefly talk about two potential applications of circular Rydberg atoms in quantum technologies, so in metrology and simulation. And then the bulk of the talk will be actually about our current experiments, because of course I'm an experimentalist. And then just a few perspectives. So let me start with telling you about Rydberg atoms. So Johannes Rydberg in 1988 gave us this empirical formula that in atoms you have energy levels who are spaced in energy basically by a quantity which is a constant multiplied by the inverse of the square of some quantum number. And this is basically how you can construct the ladder of hydrogen, for example. And very simply, actually, a Rydberg atom is any atom of the periodic table where a valence electron is put in a very excited state of quantum number n, let's say much bigger than 10. So what happens is that if you look at a given n and you apply, let's say, an electric field to lift the degeneracy, you end up with this fancy structure of energy levels. And you have some very particular levels here. You have low angular momentum states. So here I'm ranking the states by increasing magnetic quantum number. And then you have this very special state at the tip there, which is what we call the circular states. And this is what we manipulate in the lab. Okay, so let's start with low angular momentum states. And I just want to give you a few ideas, a few orders of magnitude for these Rydberg atoms. So as I said, they have a very high principal quantum number. That's how we define them. And at these very high quantum numbers, they behave like hydrogen, but with exaggerated properties, which is what makes them interesting for us. So basically, the kind of Rydberg atoms that we manipulate are on the order of a micron in size, or let's say 100 nanometers, which is huge for an atom. And they also have very large electric polarizabilities, which means that we can couple them very strongly to the microwave electromagnetic field, to their environment. So if you have some electric field or magnetic field in the environment of the atom, they will sense that. So we'll come back to that later, but that makes them great quantum sensors. And they also have very strong dipole-dipole interactions. So these giant dipoles, they interact very strongly together. And this we can use for quantum simulation, for example. So one of the perks of these atoms is that they have very long lifetimes, even though they live in a very, very excited state. Now, if I focus a bit more on circular Rydberg atoms, so these states that are at the tip there, which have the highest magnetic quantum number, they have basically maximum angular momentum, and also a large orbit, which is proportional to the square of the principal quantum number. They have several other properties that makes them especially more interesting for us than low angular momentum states, and mainly this is their long lifetime. So these low angular momentum states, they live for a few hundred microseconds, and actually the circular Rydberg levels, they live for several tens of milliseconds, which is huge for these very excited atoms. And in addition, we can encode two-level atoms between neighboring circular states, but I will come back a bit later on that when we talk about simulation. Okay, let me start first by telling you why these Rydberg atoms can be interesting for quantum metrology. And the idea again is that these huge atoms with these very enlarged dipoles, they are great sensors of their environment. And what I find particularly striking is that within the same atom, you can make a magnetic field sensor or an electric field sensor, which I think is kind of unique. So basically, I show you again for a certain principal quantum number, this lifted degeneracy of levels. So for quantum number n, you have n squared levels. And here you can see again these circular states that are at the tip there. And actually what you realize is that this state here has maximum quantum number m equals n minus 1. And actually this state here has in absolute value also maximum quantum magnetic quantum number m equals minus n minus 1. And so what happens is that the differential of these two states has a huge magnetic moment. So if you take n equal 50, principal quantum number n equal 50, if you create a superposition of this state and this state, which of course we can do using lab techniques and basic properties of quantum mechanics, well, basically you end up with an atom with a magnetic sensitivity that is well, basically 100 Bohr magnetons, which is unprecedented basically. But what's more, you also have these states here of low angular momentum, and these states are maximally sensitive to electric field. And again, if you take this state and this state, their differential sensitivity, if you create this superposition of these two states, you get an atom which is maximally sensitive to electric field. So if you can do this state engineering, you can have an incredible quantum sensor, both of magnetic field and electric field within the same atom. And this is basically what they did in our lab, what Sébastien Glaise did with his students. In some, well, I call it proof of principle, but that's because they are now going towards much more refined measurements, but these are really beautiful experiments. So basically, you have here a structure of electrodes, which allows them to control the electric field and the magnetic field in the vicinity of the atoms. And this blue arrow here is a jet of hot rubidium atoms, so that exit from an oven. We don't really care too much about these other arrows for now. They're just here to represent laser beams for excitation into these Rydberg levels. But let's say that using these kinds of quantum superpositions of Schrödinger cat states of the atom, they demonstrated an electrometer with single atom sensitivity of 30 microvolts per centimeter per square root hertz, which is, I think, the record for a single atom. And also they performed magnetometry with a single atom sensitivity of 13 nanotesla. And I will just remind you that it's a beam of hot flying atoms. So they stay in the center of the structure for very little time. So the projection for slow and trapped atoms for the sensitivity would be 700 femtotesla per square root hertz, which I think is at least one order of magnitude better than any other atomic sensor. And so if you, or at least one envisioned application of this type of metrology experiments is that you could imagine having a single carbon nanotube here, for example, under vacuum, and you have electrons that are going through this structure. And if you trap a few Rydberg atoms in a laser beam close to this structure, what you can actually do is see electrons flying by one using these Rydberg atoms. So that's how great the sensitivity is. And I think you can also envision more applications of that in, for example, life science, looking at charges and currents inside cells and stuff like that. And in link to what you guys are doing, I think one of the challenges is to be able to engineer these state superposition, both for magnetic field and electric field sensing, in a very efficient manner and very fast. And that's where quantum control, I think, is essential for these guys. But I mean, all of these envisioned applications, they rely on laser trapping of circular Rydberg atoms, which at the time of these experiments was not demonstrated yet, and that's basically 2 years ago. Okay, so now let me talk a little bit about Rydberg atoms for quantum simulation. And just very briefly, the idea of quantum simulation was given to us by Richard Feynman, who said that basically nature is quantum mechanical in essence. And if you want to make a simulation in nature, well, you better use a system that is also quantum mechanical. And he said that it doesn't look so easy, which is still the case. So Usually when we talk about quantum simulation, we talk about quantum simulation of a chain of spins like electrons in a solid or something like that. And the requirements that you need to build a quantum simulator of matter, basically, is to be able to encode a spin 1/2, to have a Hamiltonian that governs the evolution of your assembly of spin 1/2s that is as tunable as possible. When you want to explore how it works, you want to be able to tune the knobs and see how the system responds. And what you also need is a long lifetime and strong interaction to see how, for example, the system thermalizes. That's a few very important questions in condensed matter physics come from thermalization problems. And actually, I think you can already understand why Rydberg atoms will be very interesting for that, because they have extremely strong interactions from these very strong dipoles, but also, especially the circular states, they have a huge lifetime. Okay, so there are, let's say, on the market, quite a few quantum simulation platforms that are envisioned at the moment. You have, of course, superconducting circuits, trapped ions, molecules, atoms in lattices, quantum dots, nanophotonic structures, low angular momentum Rydberg states, and we want to add to this list circular Rydberg atoms. But first I want to tell you a little bit about state-of-the-art quantum simulations with these low angular momentum Rydberg states. And basically what people do in a couple of groups around the world, we'll talk here mainly about the Broways group and the Lukin group, but I think there are now probably a dozen groups that do these types of things. They create lattices or periodic structures of trapped atoms, ground state atoms. They can do this in 2D or even in 3D. And then they laser excite these atoms to low angular momentum Rydberg levels. They let the system evolve, basically. They let these strong dipoles interact together. And they look at the resulting many-body states. And they've done beautiful experiments about quenches, adiabatic sweeps. Also, they looked at some thermalization problems. But as beautiful as these experiments are, they still have some limitations, but partly because Rydberg atoms are untrapped. Actually, these low angular momentum Rydberg levels, if you try to trap them in a laser beam, they will get photoionized. So you have to be a bit careful about that. Their lifetime is limited to a few hundred microseconds, which for long-term thermalization is a problem. And they are also sensitive to blackbody radiation. Of course, these highly excited levels that are close to the continuum, if you send them blackbody photons, microwave photons, they will ionize actually, and you will lose them. And all these experiments, they are working in a 300 Kelvin environment, so lots of microwave blackbody photons around. So that's why we think circular Rydberg atoms can help. So first I need to tell you a little bit how you simulate a spin 1/2 system with circular Rydberg atoms. And it's basically fairly simple. You can just encode the spin 1/2 in two neighboring circular states. So if you take, for example, n = 50 and n = 48, so these two states that are at the tip of these two diamonds, they are separated by two microwave photons around 50 gigahertz. And essentially, if you look at this is the Hamiltonian for a two-level system. And what you can also do is apply some near resonant microwave drive. And then what that does is add to your Hamiltonian some external term, and you can rewrite this in the form that you have a longitudinal magnetic field and a transverse magnetic field, which is simulated by your microwave, basically. So just tuning this detuning here and this Rabi frequency of this microwave interacting with your two-level system. You have two knobs to crank up the magnetic field in the longitudinal and transverse direction. So if you want to look at magnetic properties of matter, that seems to be a good idea. Okay, now if you want to be a bit more refined, you add interactions between your circular Rydberg atoms. And I don't want to go too much into details here, but basically you can have two types of interactions between your circular Rydberg levels. You have a direct van der Waals type interaction if you want, dipole-dipole interaction. But what you can also have is this exchange interaction. That's the off-diagonal elements of this matrix here. And what that does is basically if you have this atom in 50C, circular state n equal 50, and this atom in circular state n equal 48, that's our spin up and spin down, well, they can just exchange energy and exchange states like this. And this is what we call this exchange interaction. So as I said, you also have this direct interaction. And if you choose your two circular states well, you can make it such that these two terms have the same order of magnitude. Then you have a really complex Hamiltonian that governs the properties of your system. And what you're essentially doing is you're creating a full XXZ Hamiltonian with completely tunable parameters. Okay, so that's why we take n equal 50 and n equal 48 and not 49, for example, for our two-level system, because then the order of magnitude of these two interactions are the same. Okay, so now basically we are armed with our full XXZ Hamiltonian. We have this longitudinal and transverse magnetic field that we can emulate using our microwave source. And we have this transverse and longitudinal spin coupling from both this direct dipole interaction and this flip-flop energy exchange interaction. And what's also very nice is that by just tuning some external electric and magnetic fields, you can basically change the relative value of these two interactions, essentially from -1 to +1. And that's quite interesting to explore basically the phase diagram of this system. So you see I plot here this Rabi frequency of the microwave source over J, the magnitude of the transverse spin coupling, versus the longitudinal spin coupling divided by J. And you have these weird phases of matter basically in your chain of circular Rydberg levels, with Néel phases, ferromagnetic phases, paramagnetic phases. You can do quenches across these phase transitions. So a very rich physics to be explored here, which you cannot do with quantum simulators who have less rich interactions, basically. So all of this comes from these two terms that you have for circular Rydberg levels. Okay, so how would this work in practice, basically? The idea is to have this chain of circular Rydberg levels here, trapped in laser beams. And one thing that you can actually notice is that these circular Rydberg states, they have only one decay channel because of selection rules, basically. So if you're in n equal 50 circular state here, The only state that you can decay to by spontaneous emission is n equal 49 circular state. So you just stay on this ladder of circular states. And actually the wavelengths of this transition between these two circular states is on the order of a few centimeters. And what that means is that if you put some plain capacitor plates around your atoms, you inhibit this spontaneous emission. You basically create a waveguide below cutoff for your atom that is about to emit microphotons spontaneously. And basically what you get is that these circular Rydberg levels that already have a long natural lifetime on the order of tens of milliseconds, well, they now have a minute range lifetime, which for simulation and for thermalization problems is really a great advantage. So as I said, we have this very, very long lifetime with a Hamiltonian that is a full XXZ model with fully tunable parameters. And this is essentially how it would look like, how it will look like, I should say, with this chain of atoms that are trapped inside these laser beams and this spontaneous emission that is inhibited. Okay, but for this to work, you see that you need laser trapping of your circular Rydberg levels. And this is something that we demonstrated very recently, and I want to talk a little bit about this right now. But maybe I think now is a good place to take a short break and ask for questions, because I'm done with the presentation part, the sort of theory part, and I'm going to delve into experiments. So if you guys have questions about the first part, now is a good time, I think.
So anyone has question?
If not, that's
well,
fine.
I would like some clarification.
Sure, go ahead.
If possible, can I ask one question about the last slide?
Absolutely, yes.
So something was not clear to me. It says that you have a very long lifetime, and what do you mean by that? You have fully tunable parameters over very short timescales, that you can change the parameters in a very short time, or that you can only apply them in short timescales?
Well, simply what I mean is that to tune the interactions, you need only to tune external electric field, and this you can do very, very fast, and especially ridiculously fast with respect to the lifetime of the atoms. So that's only what I mean. It makes it very easy to do quenches, for example, across these phase transitions.
Okay, thank you.
Sure.
So I have a question as well. You spoke about the usefulness of Rydberg atoms as sensors, but we know that indeed there are other kind of sensors, for example, NV centers, which are now very either famous and very efficient in doing their job, basically in detecting fields. So I wanted to ask you whether you could compare in terms of sensitivity the two platforms, and moreover, which one, according to you, is the most suitable to become technology in the close or far future?
Okay, so there are several aspects to the question. I'm not sure about the sensitivity of NV centers. I'm fairly sure that it's much better than these let's say proof of principle experiments of our group. That's kind of why I call them proof of principle. But I think it's a bit like comparing apples and oranges in some sense, because the thing is that in NV centers you have this bulk crystal with millions and millions of these tiny quantum sensors in it. So here you're not comparing single atom sensitivity. You just integrate all this, and this makes exquisitely sensitive quantum sensors. But I think, for example, you don't have the same degree of control as you have with a single trapped particle that you can move around. That's one thing. So here it's really one single microscopic quantum sensor that you can move around however you want. I think since these Rydberg atoms are very, very strongly coupled to the environment, to the microwave, etc., what you also have is a super high bandwidth sensor. So you can not only have a very sensitive probe, but you can also be very fast, which for some applications is very important. And again, I think I want to stress a little bit the fact that in one single platform, essentially, you have both the possibility to do magnetic field and electric field sensing, which I think is also that you need to take into account when you think about applications. This opens a lot of doors, I think.
Thank you.
I have also a question, if that's okay.
Of course. Go ahead.
So I was wondering about the tunability of the system and whether the fast changes or large changes in the amplitude and the tuning of the field would cause losses, or if the selection rules fully protect you from any loss to other states.
So I think that's a very good question. You don't lose the atoms, but what you can do is introduce decoherence. So these Rydberg levels, they are sensitive to electric fields because, as we said, they can create very great electrometers. But what that means is that, for example, if your field that you use to tune the interactions has some fluctuations, then basically you have a Stark effect on your Rydberg levels, and there you introduce decoherence. So indeed, technologically, it's mandatory to have very good control over these external electric fields and magnetic field as well. And actually, I will show you in the experiments that we have done recently. The magnetic field noise is the limitation for the coherence of these state superpositions.
Okay, thank you.
So are there any other questions up to this point?
Well, I think I will go on to the second part. And anyway, if you have questions about the first part that pop up, of course, you can ask them at the end. Okay, so now I just want to switch gears completely and tell you about the experiments that we have been doing in the lab in my group. So I'm basically working on the quantum simulation part, but of course the techniques that we develop, they also work for what the others do in other teams in the metrology team. They're applicable. And what we've been busy basically doing in the past year or so, year and a half, is to create laser-cooled circular Rydberg atoms in this cryogenic environment, so shielded from these parasitic microwave blackbody photons, and characterize the the lifetime of the coherence of these circular Rydberg atoms. And then I will tell you about laser trapping of these circular Rydberg atoms, which is, of course, a crucial step towards all these technological applications, be it metrology or simulation. Okay, so this is the experimental setup that we have. For historic purposes, we are working with an atom ship, but that doesn't matter right now. And essentially what we do in terms of atomic physics is relatively straightforward. We have a source of laser-cooled rubidium atoms that exit in a slow jet here upwards. And then here in this region, we trap them in a magneto-optical trap. So they are laser-cooled and trapped at the same time to temperatures of a few microkelvin. And we can get around 1 million atoms per realization of the experiment, let's say. But what really sets our experiment apart from what other people do is this structure around here, where you have basically these internal walls here that are thermalized by liquid helium-4. And so this is at 4 Kelvin. So that means that the environment that the atoms see, and particularly the blackbody environment, is at 4 Kelvin or a bit higher, probably because of losses. We'll talk about that later. But when you're manipulating Rydberg atoms, as we've seen, it's extremely important to be aware of these microwave blackbody photons. So what we do simply is just cool down the whole environment. That's a bit of a brute force method, but it works extremely well. And just to stress it a bit, you cannot have, of course, this liquid helium tank directly in regards with room temperature, because you would have evaporation of your helium very, very fast. And so you have an intermediate bucket here, which is filled with liquid nitrogen around this liquid helium tank. And all of this is in a vacuum chamber. So at the end of the day, what you have is a cloud, a ball of laser-cooled rubidium atoms in the ground state inside a 4 Kelvin environment. Okay, so now what you want to do is take these ground state atoms and bring them to the circular state. And this is quite a complicated procedure, but it's very efficient now. So what you do is you start from your atoms in the ground state. You first do a step of laser excitation. So this is basically where you put the energy to go to these very highly excited states. So you use optical photons, which are very energetic, of course. Then you do some adiabatic passage from this state that you reached to a state that is further away from the low angular momentum. Because something that I did not mention is that for these low angular momentum states, since the electron orbits really close to the nucleus and the remaining electrons, you have what is called a quantum defect. So you have a perturbation of these energy levels for these low angular momentum states. And as you increase the angular momentum and the electron flies further away from the nucleus, this goes away because the interaction between the electron and the core becomes negligible. So we just add this microwave transition to go away from these quantum defect problems. And then what we do is we just apply some RF field to essentially pump the atoms from this 52F state into the circular level at the tip of this manifold. And so this can be very fast and very efficient. And for this, you need very purely sigma polarized microwave, because if you have, let's say, pi polarized microwave, you will get lost in this manifold of state. You will not stay on this bottom ladder of states. And for this, we use 4 rod electrodes that are close to the atoms that sit at the center of the structure. But now we'll take you step by step through the experiment. So this is top view of a cartoon top view of the experiment. This is the atom chip, which for us is essentially a mirror. You have your cloud of cold rubidium ground state atoms here, and around you have these electrodes to perform the circularization, bring the atoms to the circular state. And then you have the detector, and I will tell you a bit more about the detection later. So what you first do is you apply your laser beams to excite these atoms from the ground state to these low angular momentum, highly excited Rydberg levels. Then once you're there, you perform the circularization. So you apply these alternating voltages on these electrodes to create your sigma polarized microwave. And then what you do is you use these electrodes in orange here to apply a huge field on the atoms. And since these atoms are in very highly excited states that are close to the continuum, if you apply a big electric field on them, you essentially just ionize this valence electron that is very far from the nucleus, and you're left with rubidium plus ions, and you can just channel these ions to a channeltron, which is just an ion counter, essentially. Okay, so then what you see on your ion counter is peaks like that, and essentially what happens is that instead of brute force applying some voltage on the atoms, we apply a voltage ramp, and the idea of that is that these different Rydberg levels, so the first that we excite with our laser, the one after the microwave transition, and also the different circular Rydberg levels of the ladder, well, they ionize at different fields because they are more or less close to the continuum. And this is essentially what you see here when you apply a voltage ramp. You see on your detector bunch of ions that arrive at different times, and that's the different Rydberg states that your atoms were in. So you have here the low angular momentum states, and here you have your circular states. And it's very nice that you can see we can clearly separate all our different circular Rydberg levels from one another. And usually we start by preparing n equal 52 circular. We can also jump to other states if we want. And we can monitor the population in all these states in a single shot detection run, basically. And so the first, let's say, basic experiment that you can do is you prepare n equal 52 at time 0. In gray here you have what is left of the low angular momentum states that we didn't bring to the circular state using our polarization. So you have this single peak of n equal 52. And then if you just wait, what happens is that this states population goes to neighboring circular states. So they go up and down this ladder. When you have spontaneous emission, you lose energy and you go, let's say, from 52C to 51C. You go down the ladder. And if you have blackbody photons that are around, then you can absorb them and you reach higher Rydberg levels. And you have basically this competition between spontaneous emission and absorption of blackbody photons. And what you see at the end of the day is that you are populating these other circular states here from your starting point of n equal 52. And this tells you the lifetime of your state, first of all, before you lose the atoms in neighboring states. But what it also tells you, if you know the spontaneous emission rate, and we do very well, it tells you the temperature of your microwave blackbody background. So it essentially tells you how many blackbody photons you have around. And so if you fit each of these peaks, the population in each of these peaks as a function of waiting time, basically, after you prepare n equal 52, when you extract the lifetime of 52C, which is 6 milliseconds. So if you remember in the first part, I promised to you tens of milliseconds. And we're not completely there yet. And that's because the blackbody temperature of the environment is not 0 Kelvin, but close to 10 Kelvin, let's say. But already 6 milliseconds is at least, well, more than one order of magnitude better than any other experiment involving Rydberg states, basically. And that's thanks to these circular states that are shielded from decay channels and this blackbody environment that we can manage really well. Okay, but this is not enough. Essentially, your state lives for a long time, but if you want to do useful quantum technologies, you also need to be able to build quantum superposition of states that live for a long time. This is what we do when we assess the coherence of our Rydberg levels. But first, I want just to mention that we have very efficient ways after we have prepared, let's say, n equal 52, to navigate between these manifolds of states just by applying microwave. So I told you that these Rydberg atoms, they are very sensitive to microwave, and we can use that to our advantage and basically transfer the atoms from 52C to, for example, 51, 50, or 53. However we want, we can do 3 photon transitions in one go, for example. And this is what you see here, these spectra that show you the transfer from n equal 52 to n equal 49, for example, here, n equal 52 to 50, 52 to 51, and 52 to 53. This gives you great diagnostic tools to do spectroscopy. And it also allows you to prepare arbitrary superpositions of, let's say, here 52 and 51 or 52 and 49. So what we did is basically we prepared a superposition of 52 and 50. And we let this superposition evolve as a function of time, and we see how the fringes decay, the Ramsey fringes decay. And so that's the first experiment that we did, and we got what you probably know as a T2 star Ramsey contrast decay of 45 microseconds. And then if we do a bit of a more refined experiment, we put between our two pi/2 pulses that create and then recombine this state superposition, a pi pulse. That's called the spin echo experiment. Then after this decay, we see a revival of oscillations, and if we fit the amplitude of this revival as a function of the time of this echo pulse here, we get what is known as the T2 of the experiment, basically, which is 260 microseconds. And that's essentially our coherence time for this 52C plus 50C superposition. So one thing that you can notice is that it's something like an order of magnitude smaller than the lifetime, which of course is not what we want in the end. But the good news is that we figured out that this decoherence is essentially caused by magnetic field noise. And the good news also is that the other good news is that we took absolutely no precaution whatsoever to stabilize the magnetic field in the experiment. So this is really an experimental problem that is actually reasonably easy to solve. So this is the limitation right now, but it won't be in a few months, let's say. Okay, so basically, so far I've showed that we can have laser-cooled circular Rydberg atoms, and we have characterized their lifetime and their coherence. And now for enabling these quantum technologies that I talked about, we need to laser trap these cold atoms. This is what we demonstrated. But first, I have to tell you a little bit how laser trapping of a Rydberg atom works, because maybe you know that for ground state atoms, you use the polarizability of the atom in a laser field to do the trapping. But here the mechanism is a bit different, because essentially what you have when you have a circular Rydberg atom with this core and this electron that is orbiting the core far away is an almost free valence electron. And if you apply an oscillating electric field on a free electron, what you get is what is called the ponderomotive energy shift. And this is a positive shift that scales with the intensity of your laser field. And what that means is that basically, if you shine a laser beam on your free electron, it will be a low field seeker. Now, then what you can imagine to do is have some kind of donut beam with dark light, dark in the center, surrounded by light. And then you will trap this free electron. And then what happens is that since the core is bound still to the electron by the Coulomb interaction, you end up trapping the whole atom. And that's, I think, it's kind of cool that you can think of it, that you are trapping this electron and the rest of the atom, which is much bigger, just follows it. So that's what we want to do. We want to create this vortex beam and trap the Rydberg atoms at the center in the dark region here. So these are set up to do that. Essentially, we use this device that is called a spatial light modulator, or SLM. And the idea is that you have just simply a liquid crystal display here, the same as you have in your computer screen, essentially. And when you shine light on this device, in each pixel you can apply a different electric potential, and this locally changes the phase of the light that bounces on it. So you imprint a local phase on different spatial pixels of your laser beam, essentially. And then if you choose the phase pattern here carefully, at the focus of a lens, you get essentially the Fourier transform of this pattern imprinted on your laser beam. And if you're smart enough, you can create a donut. Fortunately, we were smart enough for that. And essentially what I show you here is this trapping beam, the big red beam here, which goes around this cloud of cold Rydberg atoms. Of course, this is inside these 3-layer buckets, this cryostat that I told you about. And then, as I told you, we can detect the ions that go to our detector. And the only trick with this was that the alignment between our trapping laser and our Rydberg excitation laser was crucial, and this is what gave us the most difficulty. Okay, now I have to actually demonstrate to you guys that we have indeed trapped the atoms. And it turns out that this is not so easy to do, basically because our detection is non-spatially selective. So if you remember, we just have these Rydberg atoms, and we rip off this electron by applying an electric field, and we just take the ions and count them in a detector. But this is really not spatially selective, and if you want to demonstrate trapping, you have to essentially prove that your atoms, they stay in the same region of space as a function of time. Essentially, that's what it boils down to. And so the idea that we had is to basically use this spectroscopy between Rydberg levels that I showed you a few slides ago to basically imprint the spatial dispersion of the atomic cloud into a spectral dispersion, basically. So what we do is we apply a gradient of electric field, and we interrogate an electric field sensitive transition between Rydberg levels. And so if your cloud is extended in this gradient of electric field, essentially your different atoms in your cloud, they will resonate at different frequencies with the microwave because of the Stark effect. And you will have a broad line. So that's what I show here, this red broad line. But if you've managed to trap your atoms, then your line will be narrow because you have a small cloud in this gradient. So then the idea is to create these circular states, laser trap them, and check the width of this line as a function of wait time. And so if the atoms are untrapped, they fly away, and then this line gets broader, and if they are trapped, this line stays narrow. Okay, so that's why I show you. That's what I show you here. In blue, you have the spectroscopic line when the trapping laser is on, and this is after 2 milliseconds of wait time. And in red, you have the spectroscopic line if the laser trapping is off. And then if you plot the width of this transition as a function of wait time, well, you see very clearly when the laser beam is off that the cloud increases and this line broadens. And when the laser beam is on, this line stays very narrow. So this shows you that we can laser trap our circular Rydberg atoms. So far it's only 2D, but we will extend it to 3D very soon. And usually when you do these trapping experiments, one essential parameter that you want to look at is the oscillation frequency of the atoms in the trap. And this we have also characterized, and it's on the order of 1 kilohertz for our current parameters. And then one final thing that I want to mention is that, of course, this laser trapping, you can imagine that it perturbs the energy levels of your Rydberg atom. And essentially, you might be worried that it introduces decoherence. And this we checked for by doing spectroscopy, basically as narrow as we can on a circular to circular transition. So again, the spectroscopy is a great diagnostic tool. And essentially, we see no difference between the width of this line if the trap is on or if the trap is off. So that gives essentially a bound on the fact that coherence is not affected by the trapping light, which is great news because, again, if you introduce huge decoherence on your quantum superpositions when you do this laser trapping, then all of these Rydberg atom technologies, they won't work. Okay, so I just want to conclude now on the future of the experiment. So essentially, I showed you that we have great promise for Rydberg atoms as quantum technologies in the future, and we are building first steps towards these directions by having laser-cooled circular Rydberg atoms and trapping them in laser beams. And what we want to do in a very near future, hopefully before the end of the year, is first do 3D trapping of these atoms, and not simply 2D in a tube. But using your spatial light modulator, you can also engineer light patterns that create these kinds of little bubbles of light, little pockets of light with dark at the center, and you have then 3D confinement of your Rydberg atoms. And this we want to do using high numerical aperture lenses inside a vacuum to trap individual Rydberg atoms. So this is what we will do on the short time scale. Then we can characterize this interaction between Rydberg atoms that is essential for the quantum simulator. And then on the more long-term plans, basically, you want to have these trapped Rydberg atoms, and you also want to demonstrate this spontaneous emission inhibition that I talked about, because it will be crucial for the simulator in the long run. And so basically we have several experiments in the lab working in parallel towards this goal. We have room temperature experiments to demonstrate this spontaneous emission inhibition. And then we have cryostat experiments to demonstrate this trapping. And the long-term plan, of course, is to put everything together and to demonstrate this quantum simulator. So these are the permanents that are working on these different experiments in parallel. And finally, I want to thank you for your attention and thank my lab mates for their hard work. And I await your questions. Thanks.
So thank you, Maxime. Are there any questions?
Yes, I had one.
Sure.
Yeah, okay. So my question is I was just curious, for the cooling of the Rydberg atoms, could you also do like evaporative cooling instead of using cryostat? Is that something?
Okay, one thing that I can say, essentially these are two different types of cooling, let's say. So evaporative cooling is something that we indeed envision when you prepare this chain of Rydberg atoms. But you also need to cool the photon environments of your atoms, and for this you need the cryostat. So the evaporative cooling will work on the external degrees of freedom of your atoms, if you want. But the internal degrees of freedom that are perturbed by these microwave blackbody photons, this you need the cryostat to take care of.
Okay. And I have another question, but this was from the first part, before the experiments. So that you had a slide about the phase transitions.
Yes.
Yes, so in this one, I was just wondering on the x-axis, so you have the microwave radiation, is the ratio of the microwave radiation with 4 times the interaction. Like, as in, I was wondering, like, why 4 times, or?
That's a good question. I'm not sure actually. So we have strong theory collaborations, and these plots, they are done by our theory collaborators. And indeed, this 4J is also in here. I think it's just in the math of the problem that it's actually 4J that is the relevant parameter. But I'm not sure physically if I can give you an explanation for why that is.
Oh, it's fine, yeah. Okay, thank you. Thank you for the talk also,
Sure.
yeah. It's very nice.
My pleasure.
So I have a question concerning the lifetime. You write exactly in this slide plane parallel capacitor, which I suppose will improve the performances of a Rydberg platform, especially enhancing the lifetime. And my question is, which order of magnitude in terms of lifetime can be envisioned once placing a proper capacitor, roughly?
So the number that we usually give, which is of course theoretical, since we've not measured that yet, is on the order of a minute for a single atom. And then if you have a chain of 60 atoms, that's then 1 second for your whole chain. So if you look at the order of magnitude of the interaction, which is in the kilohertz range, but you can even crank it up further, that's essentially on the order of, let's say, 10 microseconds. So then what you get is that you can see 10 to the 5 cycles of interaction between these Rydberg atoms during this 1 second for your whole chain of 60 atoms, which is completely unprecedented for quantum simulation platforms, basically.
Thank you. Other questions?
Yeah, so I have a couple of questions. So first of all, thanks for the great talk and for showing us this really cool experiment. I hope it goes well.
Yes.
So a couple of things. So first, on one of the latest things that you were showing was this point that you don't see the line width changing with the trapping laser on or off. How do you measure the line width when the trapping laser is off? I mean, aren't the atoms gonna not be trapped at that point?
So that's a very good question. We use actually a different transition. So this is a bit in the details, but when we do this expansion experiment, we use a transition between a circular state and what we call an elliptical state, which is a state that is not circular but close to circular. And actually, this transition is very sensitive to electric field, and that's why when you apply a gradient of electric field, you see this broadening. But if you choose the transition between two circular levels that is extremely insensitive to electric field, then you essentially get rid of all these problems. You can also minimize this gradient. We crank it up to demonstrate the trapping, but you can tune it down using the electrode structure that we have around the atoms. And so essentially this line here, it's very insensitive to electric field.
Okay.
So it can only be perturbed by light shifts, if you want, from the trapping laser. That's what we are worried about here.
But still, I don't know if I still understand how what happens to the atoms when the trapping field is off.
Well, they just fly away.
Okay.
In this sort of inhomogeneous electric field. But this transition here, this particular transition between two circular states, it doesn't see these homogeneities because it's not sensitive to electric.
Okay, now I understand. Thanks. Yeah, okay, that makes sense. Then, okay, I had another question, which is, so when you showed these broadening of, or at least population transfers from the prepared 50 circular state to you wait some time and you see that all the other circular Rydberg state get populated. It seems symmetric. So if does this mean that this broadening is caused by blackbody radiation rather than by the temperature of the atom itself?
Indeed.
Okay.
Exactly. This is purely blackbody.
Okay. Okay, so that means that the transitions going both up and down are both present in the blackbody radiation.
Yes.
Okay. Okay, that makes sense.
And essentially it means also that basically spontaneous emission and absorption have the same kind of order of magnitude of rate.
Okay. Yeah. Yes. And okay, so one final question, if there's still time, which is what limits your fidelity for the transfers between the circular Rydberg states? It was going to like 80%, it seemed.
Yes, I think you assume these ones.
Yes.
So I have to say that not all of these curves are best effort, let's say. But it's true that usually we are limited to about 90%. And I think I can give you several reasons. Well, first of all, you have the fact that you shine some microwave on your atoms, and essentially your atom cloud, it has a certain size, and the microwave is not homogeneous for the different atoms in this cloud. So you have a gradient of microwave power, for example, across the cloud, and this causes some infidelity in the transfer. And then you can also have all these types of noise that we mentioned, like electric field noise or magnetic field noise. These can also reduce the contrast of this transfer.
And this first reasoning that you gave, that there's a cloud and the microwave field might not be the same over the whole cloud, that error should disappear once you have these trapped Rydberg atoms, right?
You're absolutely right.
Okay. Okay. Nice.
Yeah, these trapping single atoms, in some sense, it's challenging, but it also comes with its own perks that you have a system that is extremely localized in space, and so you are much less sensitive to these inhomogeneities in your apparatus, essentially.
Yep. Makes sense. Thanks so much.
Sure.
Other questions? Okay, if not,
So sorry, I didn't want to hug all the time, but I did have one other question, which is a bit more broad, which is how does like what's the process that gets an experimentalist team started on such a project? Because I guess there's some idea of some desire of wanting to do this type of experiment, and then some theory work to check if it's possible. What are the steps? What are the timelines? It's a bit of a broad question, but I'm just interested in what happens.
Well, so I think there is also a historical factor, let's say, because the head of the lab before Michel Brune was Serge Roche, and together with Michel and Jean-Michel, they did a lot of experiments with these circular Rydberg levels, to mainly in the context of cavity quantum electrodynamics. So it's essentially using this great sensitivity of these states to microwaves and putting them in microwave resonators and demonstrating some beautiful concepts of quantum physics. Essentially thought experiments that were put forth by the great thinkers of quantum mechanics 50 years ago, and then they demonstrate this in the lab. So that was I think the historical reason for using these circular Rydberg states. And then I think now the lab is really shifting towards this let's say, more modern atomic physics experiments with laser cooling and trapping and all that, because these are really enabling technologies. So that's the direction now. And actually, probably I'm not the right person to ask why this direction was chosen. But I think there are smart people like Sébastien and Michel and Jean-Michel that thought about these applications of circular Rydberg states. But essentially, these are beautiful physical objects, right? I mean, this electron that orbits far from the nucleus on a perfect circle, and the applications, essentially, they are built in the system itself. If you think about it, okay, I have this atom with 100 Bohr magnetons. Well, it makes sense that I would use this as a magnetic field sensor, right? Then it's a single atom with exquisite sensitivity to magnetic field. And then I have this huge, Rydberg manifold, and I can engineer state superpositions in this where I have states that are maximally sensitive to electric field or magnetic field. I think the beauty of the physical system itself shows you the applications, in a sense. I don't know if that answered your question.
No, it's a good answer. Thanks. Thank you.
Yeah.
Other questions? Okay, if not, I wish to thank again Maxime for being here and for this fantastic talk, which makes, I think, very clear the topic. And again, I check that there are nobody else wishing to ask questions, and in such case, I interrupt the recording. And thank you all again for joining.
Yeah, thank you for listening to me.
Thank you for your presentation.
My pleasure.